Hey, 9.6 notes on ratio test and root test. We're going to start off with the ratio test. We're going to use the ratio test to determine convergence or divergence. So this is yet another test that we need to be familiar with. So the ratio test is a test that determines whether a function is going to converge absolutely. So given that we have a rule of sequence, a sub n, we let that be a series with non-zero terms. If the series converges absolutely, the series will converge absolutely if the limit as n approaches infinity of a sub n plus 1 over a sub n, or the absolute value of the quotient, is less than 1. So what we're going to do is we're going to divide the subsequent term by the previous term. So this is similar to the limit comparison test, except that we are using the same we're using the same series. This is especially good for dealing with functions that grow at a very rapid pace, like the exponential or factorial series. So we take the ratio of the subsequent term divided by the previous term, and if the absolute value of that is less than 1, then we can say that the series will converge absolutely. But if the ratio is where the limit as n approaches infinity, if that ratio comes out to be a value that's greater than 1 or to infinity, then we know that the series will diverge. And finally, the ratio test is inconclusive if the limit of the ratio is equal to 1. So again, it's particularly useful for series that converge rapidly, such as factorials or exponential functions. So let's look at the first example here. The sum of 2 to the n over n factorial. Again, we always want to choose to use the nth term test first. In this case, it's inconclusive because the limit of this quotient will go to 0 because the n factorial is growing at a faster rate than the exponential function. So inconclusive. So the way that we're going to go about using the ratio test is we're going to be replacing the n with the n plus 1, or replacing n with n plus 1 in order to arrive at the n plus first term, or the next term in the sequence or in the series. So we're going to find the next term in the series by replacing the n with n plus 1. So this becomes 2 to the n plus 1 over n plus 1 factorial. That's the next term, divided by the current term, which is given here, 2 to the n over n factorial. Now, if we're dividing complex fractions, we can multiply by the reciprocal of the denominator. So 2 to the n plus 1 over n plus 1 factorial times n factorial over 2 to the n. And we're going to see some things cancel out here. 2 to the n plus 1 is the same thing as 2 to the n times 2 to the first. The 2 to the n will cancel out, leaving us with just a 2 in the numerator. And then the n plus 1 factorial is the same thing as n plus 1 times n factorial. So the n factorials will cancel out, leaving us with n plus 1. Now, if we simply take the limit of our remaining quotient, 2 over n plus 1 as n approaches infinity, we know this will give us 0, and 0 is less than 1. So we know that our series will converge absolutely by the ratio test. Okay, next example here. Again, the nth term test will be inconclusive. Looks like the 3 to the n is going to grow faster than 2 to the n, but then there's n squared here, so we're going to have to go through, let's go through ratio test here. Again, what we can tell, that is a good possibility that ratio test will be good for this because we have factorials and exponential functions. So to find the next term, we're going to replace n with n plus 1, so n plus 1 squared times 2 to the n plus 2 all over 3 to the n plus 1. And this, we're going to put this all over the original series, which is going to be the same thing as multiplying by the reciprocal. So 3 to the n over n squared times 2 to the n plus 1. let's see here, 3 to the n plus 1 is the same thing as 3 to the n times 3. So 3 to the n will cancel out, leaving us with just 3. The n plus 1 squared over n squared will have to stay. But the 2 to the n plus 2 is the same thing as 2 to the n times 2 squared. 2 to the n plus 1 is the same thing as 2 to the n times 2 to the first power. The 2 to the n's will cancel out, leaving us with just a 2 up in the numerator. And we see that we can expand this out to be n squared and this n squared as well. The degrees are the same. We can just take the leading the ratio, the ratio of the leading coefficients as n approaches infinity, which is 2/3. So 2/3 is less than 1, and less than 1 means that, again, our series will converge absolutely because of the ratio test. Okay, third example here. The sum of n to the nth power over n factorial. So technically, we can look at this and see that the factorial is going to grow at a faster rate than the exponential function. So this should be, so actually, this will go to 0, but which means that the nth term test will still be inconclusive. So we have to go through our ratio test here. So replace all the n's with n plus 1. So n plus 1 raised to n plus 1 all over n plus 1 factorial times the reciprocal. So n factorial over n to the nth. And if I expand this out, this is n plus 1 to the nth times n plus 1 times n factorial. The denominator can be rewritten as n plus 1 times n factorial. And then I bring down the n to the nth. The n plus 1s will cancel out. The n factorials will cancel out, leaving us with just n plus 1 over n raised to the nth. And if I expand this out, this should be a little more familiar if I write this as separate fractions. 1, n over n is 1. 1 over n is 1 over n raised to the n. This should be recognizable as equal to e. Now, e is 2.7, which is greater than 1. So therefore, by the second condition, by the second rule here, if the limit of the ratio is greater than 1, then we know our series will diverge, okay, by the ratio test. All right, the fourth one here, square root of n over n plus 1. Let's go through ratio test again. Replace the n's with n plus 1. So square root of n plus 1 over n plus 2 times, or divided by square root of n over n plus 1, which is the same thing as multiplied by n plus 1 over square root of n. Now, if I combine this together, I'm going to be left with something that I just can't cancel out, and the ratio test will end up being inconclusive. However, we see that we have alternator here, so we can maybe use the alternating series test. If we can just show that the a sub n will go to 0, then that's enough to show that the series will converge. So square root of n over n plus 1, we see that the n plus 1 is growing at a faster rate than the radical. So therefore, this rule of sequence will go to 0 as n approaches infinity. And this is enough for us to show by alternating series test that the series will converge. Okay, last one here. N plus 1 factorial over 3 to the n. We see that the numerator is growing at a faster rate. The factorial is growing at a faster rate than the exponential function. So actually, by the nth term test, this series will diverge. Okay, so no need to do ratio test. Nth term test will be able to take care of this for us.